All right, let's talk about the microscopic magic that is literally powering everything around us right now. I'm talking about semiconductors.
I mean, really think about it for a second. That phone in your hand, what actually makes it smart? How does it do, well, everything it does? The answer is kind of wild. It's both way simpler and way more complicated than you probably think. See, it's not just one thing, it's billions of things. Inside that phone, you've got something like 8 billion, with a B, tiny little switches called transistors, all firing on and off on a single chip. And the secret sauce? The material that makes every single one of those switches possible? That's the semiconductor. So, if we really want to get how your phone works, we've got to zoom in. And I mean way in. We're going past the screen, beyond the battery, all the way down to the atoms that make up the materials themselves. And this is where we meet the hero of our story. It's the special material that's, well, it's not a great conductor like copper, and it's not a great insulator like rubber. It's in this perfect sweet spot, right in the middle. You could call it a Goldilocks material. And that unique, just right property, that's the key to everything. Okay, so to get why that matters, we have to get a little nerdy and talk about electrons and energy. So in any solid material, right, electrons can only exist in these specific energy zones, which we call bands. Now, there are two you need to know. The valence bands, that's where electrons are kind of stuck, bound to their atoms. And then there's the conduction band. This is the fun zone, where electrons are free to move around and create an electric current. But the real secret isn't in the bands themselves, it's the space between them. And this chart here shows you exactly what I'm talking about. That space is called the energy gap. Now look at conductors, like metals, there's basically no gap at all. The bands overlap, so electrons can just jump around freely, easy. Then you have insulators. The gap is massive. It takes a ton of energy for an electron to make that leap. But then, look right there in the middle, semiconductors. The gap is small, but it exists. And that is the whole point. It's a gap we can actually control. And control really is the magic word here. Because, a pure semiconductor on its own is interesting, I guess, but not super useful. We need a way to mess with it, to manipulate its conductivity. We need to be able to tell it exactly when to let electricity flow and when to stop it. We basically need to hack the material itself. And that hack, it's a process called doping. And yeah, I know, it sounds a little shady, but it's pure material science, I promise. What we do is we deliberately sprinkle in just a few impurity atoms into an otherwise pure crystal, like silicone. Think of it like adding one tiny drop of food coloring to a huge jug of clear water. That tiny change, it changes absolutely everything. So we've got two main flavors of this doping. First, you can add an impurity that has an extra electron, like arsenic. This gives us what we call N-type material. N for negative, because it has all these extra free electrons. Or you can do the opposite. You can add an impurity that's missing an electron, like boron. This creates a vacancy, an empty spot where an electron should be. We call this a hole. And you can think of this hole as a positive charge, just waiting for an electron to come fill it. That gives us P-type material. So boom, now we have two new versions of our semiconductor, one with extra electrons and one with extra holes. Okay, now this is where the real magic happens. So what if we take a piece of our N-type material and we stick it right up against a piece of our P-type material? When these two meet, we create something called a p-n junction. And I'm not exaggerating when I say this little junction is the fundamental building block of pretty much all modern electronics. So the second these two materials touch, it's instant chaos. All those free electrons on the N side see the empty holes on the P side, and they're like, I'm out of here. They rush across the border to fill in those gaps. But wait, when they leave behind positively charged atoms on the N side, and when they fill the holes, they create negatively charged atoms on the P side. This creates this really thin layer right at the junction where there are no free electrons or holes left. It's been completely depleted of charge carriers. And this depletion region creates its very own electric field, a barrier that basically says, all right, party's over, and stops any more electrons from crossing. And this barrier, this self-forming wall right at the junction, that's the whole point. It's a natural built-in gate. And by default, that gate is slammed shut. No electricity can flow. But what if we could find a way to open and close that gate whenever we wanted?
Well, it turns out we can. We can control that gate just by applying a little bit of electricity, an external voltage. Depending on how we hook it up, we can either push that barrier down and open the gate, or we can build the wall even higher and lock it tight.
Okay, check this out. If we hook up the positive end of a battery to the P side and the negative end to the N side, we call this forward bias. Our voltage literally pushes against that barrier, shrinking it down to nothing. The gate flies open and boom, current flows right through. But if we flip the battery around, reverse bias, our voltage actually reinforces the barrier, pulling it wider and making it even stronger. The gate slams shut and basically nothing can get through. It's a dead end. So what did we just build? We've created a one-way street for electricity. It can go this way, but not that way. The source material puts it perfectly. It says a PN junction diode primarily allows the flow of current only in one direction. It's basically an electronic valve. Okay, a one-way valve for electricity. Cool, but so what? Why is that such a big deal? Well, to answer that, we need to zoom all the way back out. Let's leave the world of atoms and go back to something you use every single day, the power outlet in your wall. See, the power coming out of that socket is alternating current, or AC. That means the electricity isn't flowing in one steady stream. It's sloshing back and forth, changing direction 50 or 60 times every single second. Now, that's great for sending power over long distances, but for your phone, it's total chaos. It's completely useless. Your phone, your laptop, all that sensitive stuff needs a nice, smooth, steady flow of power. It needs direct current, or DC. So the big question is, how do we get from that crazy back and forth AC from the wall to the calm one-way DC that our devices actually need? You guessed it. We use our little one-way valve. That PN junction diode acts as what we call a rectifier. When that messy AC current comes along, trying to go back and forth, the diode says, nope. It only lets the current through when it's going in the forward direction. When the current tries to go in reverse, the gate slams shut. It literally just chops off the entire backwards half of the wave, turning that chaotic flow into a pulsating, but definitely one-way flow of electricity. And that one simple job, that conversion from AC to DC, performed by a tiny PN junction inside that little power brick you plug into the wall, that is the absolute first, most critical step in powering every single electronic device you own. It all starts with that one-way street at the atomic level. So that leaves us with a final thought to chew on. If just one of these simple junctions can act like a gate, a one-way valve, what happens when you string together millions or even billions of them on a single chip? What kind of complex logic, what kind of computation, what kind of thinking can you build? Well, that's how you get from a simple diode to the actual brain inside your smartphone. Just amazing stuff. Thanks for joining me on this deep dive.